Hello everyone. Today's topic for our presentation is semiconductor chip packaging, and we are going to discuss different types of semiconductor chip packaging. We are group 4, and I'm Riya Shah. We have with us Amit Samarth and Prem Shazode. Each one of us will be discussing one of the type of chip packaging. So, what is semiconductor chip packaging? It is a crucial aspect of the semiconductor manufacturing process. As it involves including the integrated circuit or semiconductor chip in a protective package from the outside world. It also safeguards the chip from external elements such as moisture, dirt, and mechanical stress. The packaging process also plays a significant role in heat dissipation and overall reliability of the electronic device. So the first one is DIP package, that is dual inline package. This is the simplest of among all. So DIP or dual inline package is a type of integrated circuit packaging that features two parallel rows of metal pins called dual inline pins on either side of the rectangular shaped circuit. DIP packages can be soldered onto a printed circuit board or inserted into a DIP socket. DIP chips have two rows of pin and require insertion into DIP socket on a chip carrier or can be directly soldered onto a printed circuit board. DIP packages have been widely used for DIP switches, LEDs, 7-segment displays, ICs, and bar graph displays, etc. There are four types of dual inline packaging that I will be discussing later. First, let's see the DIP structure. As you can see, the second image of DIP structure as given on the slide. The DIP package consists of a lead frame, a package substrate, a silicon die, gold wire bonds, and a polymer overmold. So what each of does is the lead frame is a thin metal frame that holds the silicon die and provides electrical connection to the outside world. The package substrate is a thin piece of insulating material that supports and electrically connects the lead frame and the silicon die. The third one is the silicon die, which is the heart of the DIP package, containing the electronic circuitry that performs the desired function, which is given by the external world. The gold wire bond connects the silicon die to the lead frame, allowing electrical signal to flow between the silicon die and the outside world. The last one is polymer oval mold. That is a protective coating that covers the lead frame, a package substrate, silicon die, and a gold wire bond. It provides mechanical protection, prevents moisture, and improves the overall reliability of the DIP packaging. So, as I mentioned earlier, there are four types of DIP package. Two of them are mentioned on the slide. First one is ceramic DIP, and second one is plastic DIP. So, ceramic DIP is has better electrical performance and higher resistance to heat as compared to plastic DIP, and also moisture and shock. Plastic DIP, on the other side, consists of two parallel rows of pins that provide insulation and protection for the ICs. Another two is shrink plastic DIPs and skinny DIPs. So shrink plastic DIPs features with a small lead pitch of in 1.778 mm, and skinny DIPs come with a width of 7.62 mm and a pin center distance of 2.54 mm. So let's see now what are the pros and cons of dual inline package. First pros, it is simple and low cost. As compared to others, it is easy to manufacture and assemble for mass production. Compatible with through-hole mounting techniques, it also has kind of good heat dissipation, easy to replace without damaging the surrounding components. Now cons: DIP package takes up more space on the circuit board compared to other packaging like types like SMT. They are not suitable for high densities applications since pin packaging spacing is limited. And another is DIP are not rugged as other packages type and can be damaged by mechanical stress such as bending or twisting. And the last one is they can be also affected by temperature fluctuation, which can cause the pin to expand or contract and potentially leads to solder joint points. The next will be explained by Amit, which is ball reader.
Yes, so now moving on to the ball grid array, which is also known as BGA packaging. So what is the BGA packaging? So it is a type of surface mount packaging, usually acts as a chip carrier that is used for integrated circuits. BGA packages are used to permanently mount devices such as microprocessor. A BGA can provide more interconnection pins that can be put on a dual inline or flat packages. Basically, in the BGA, the whole bottom surface of the device can be used instead of just the perimeter, as you have seen in the dual inline packages. In this, the traces connecting the packages leads to the wires or the ball, which connect the die to packages that are averagely shorter than with the perimeter only type, leading to a better performance at high speeds. So, how was the BJA been developed? So, BJA is generally a descendant of the pin grid array also only. In which it has one face covered or partly covered with pins in a grid pattern, which in operation conduct electrical signals between the integrated circuit and the PCB on which it is placed. In a BJA, the pins are replaced by the pads on the bottom of the package, each initially with a tiny solder ball stuck to it. These solder spheres can be placed manually or by automated equipment and are held in place by a tacky flux. The device is placed on a PCB with copper pads in a pattern that matches the solder balls. The assembly is then heated, which can be either conducted in a reflow oven or an infrared heater, which melts the ball. Then the surface tension causes the molten solder to hold the package in alignment with the circuit board at the correct separation distance. While the solder cools and solidifies, it forms the solder connections between the device and the PCB. In more advanced technologies, solder balls may be used on both the PCB and the package. Various advanced technologies are also being developed, like multi-chip modules. Solder balls are used to basically connect two packages. So moving on to the advantages, one of the most significant advantages that for which ball grid array is used instead of a dual inline or quad flat package is high density. So as you can see in the diagram, the whole surface area is used instead of the peripheral or the perimeter uh, of the IC. So the BJ is the modern solution to the problem in which we can produce a miniature package for ICs with many hundreds of pins. Uh, then, but this was also causing difficulties for the soldering packages. As package pins got closer together, the danger of accidentally bridging adjacent pins with solder also grew. Uh, Next advantage is heat conductance. A further advantage of BJA packages over packages with discrete leads is the lower thermal resistance between the package and the PCB. This allows heat generated by the integrated circuit inside the package to flow more easily to the PCB, preventing the chip from overheating. The next advantage of ball grid array is low inductance leads. The shorter an electrical conductor, the lower its unwanted inductance, a property which causes unwanted distortion of signals in high-speed electronic circuits. Ball grid arrays with their very short distance between the package and the PCB have low lead inductance, giving them superior electrical performance than pin devices such as dual inline package or quad flat package. Then we'll move on to the disadvantages. So first major disadvantage is its lack of compliance. So what does lack of compliance means? So a disadvantage of ball grid array is that the solder balls cannot flex in the way that longer leads can. So they are not mechanically compliant. As with all surface mount devices, bending due to the difference in coefficient of thermal expansion between PCB substrate and BJE, or flexing and vibration, can cause the solder joints to fracture. Thermal expansion issue can be overcome by matching the mechanical and thermal characteristics of the PCB to those of the package. Typically, plastic BGA devices more closely match PCB thermal characteristics than the ceramic devices. Another way through which the mechanical stress issues can be overcome is by bonding the devices to the board through a process called underfilling, which injects an epoxy type mixture under the device after it is soldered to the PCB, which effectively glues the BG devices to the PCB. There are several types of underfill materials which are used. Uh, uh, an additional advantage of underfill is that it limits thin whisker growth. Then another type of disadvantage is its difficulty of inspection. So once the package is soldered into place, it is difficult to find soldering faults. X-ray machines, industrial CT scanning machines, spatial microscope, and endoscope to look underneath the solder package have been developed to overcome this problem. If a BJ is found to be badly soldered, it can be removed in a rework station, which is a jig fitted with infrared lamp, a thermocouple, and a vacuum device for lifting the package. The BGA can be replaced with new one, or it can be refurbished and installed on the circuit board, but it is very costly. Due to the cost of visual X-ray inspection, electrical testing is very often used instead, in which very common is boundary scan testing using an IEEE 1149.1 JTAG board. Uh, the cheapest technique which have been developed is referred to as die and pry process. This process includes immersing the entire PCB or just the BGA attached module into a die, and after drying, the module is prived off and the broken joints are inspected. If a solder location contains the die, then it indicates that the connection was imperfect. Next disadvantage is difficulties during circuit development. During development, it is not practical to solder BGAs into place, and sockets are used in place, but they tend to be unreliable. There are two common types of sockets. The more reliable type has spring pins that push under the balls, although it does not allow using BGAs with the balls removed, as spring pins may be too short. Then another disadvantage is cost of equipment. Expensive equipment is required to reliably solder BGA packages. Hand soldering BGA packages is very difficult and unreliable, usable only for smallest packages in the smallest quantities. However, as more ICs have become available only in lidless or BGA packages, various reflow methods have been developed using inexpensive heat sources such as heat guns, endomostic toaster, ovens, etc. And then based on various applications or requirements, various variants have been developed of the ball grid array. Some of the most common are CABGA, which stands for chip array ball grid array, or CTBGA, which stands for thin chip array ball grid array, or FCMBGA, which stands for flip chip model ball grid array, or micro ball grid array, low profile fine pitch ball grid array, new fine ball grid array, and various others have been developed according to their purposes and requirements. So, next type of packaging will be explained by Prem. Over to you, Prem.
Yes, the next type of package is a QFN package. So QFN is stands for quad flat no lid package. It is a lidless package that comes in a small size, and also it offers a moderate heat dissipation in PCBs. Like any other IC package, the main function of the QFN package is to connect the silicon die of the IC to the circuit board. Now we will see what's inside a QFN package. So in this diagram you can see the QFN packages come with a die that is surrounded by the two lead frames, and these lead frames are made up of a copper alloy with a matte tin coating. The die and the frame are usually connected to each other using the wire bonding. And like here in this diagram you can see the bond wires. So here the bond wires are used to connect the silicon die and the lead frame. So the copper is usually preferred for wire bonding. Some manufacturer also use the flip chip technology for the interconnection. So the metallized terminal pads are located at the bottom surface, and these terminal pads are present along the four edges of the bottom surface, and also it like these edges provide the electrical interconnections to the PCB. The bottom side of the package consists of an exposed thermal pads, and these pads provide an efficient heat path to the PCBs. The exposed pad provides the exposed pad enables the ground connection as well, and the QFN package is soldered to the circuit board at the exposed pad. So now we will see the types of the QFN package. So the first type is the punch type, and the second type is son type. In punch type singulation, the package is molded in single mold cavity format, and that is separated using a punch tool. This means that only a single package is molded into shape using the method. And in son type, the packages are molded using the mold array process. This basically the mold array process involves cutting a large set of the packages into the parts, and a final saw process helps to separate the son type packages into individual packages. Now we will see the what are the advantages of the QFN package and disadvantages of the QFN packages. So the advantages are the QFN packages are lightweight and easy to handle, and the bond wires are short, and also these packages are easily available at low cost. And the disadvantages are this QFN packages has a less number of pins than the QFP packages. So QFP is a quad flat package, and the inspection of the QFN package under the microscope is difficult, and also these packages are difficult to repair when they gets breakdown. Next slide. So now we'll see the different types of QFN package terminal pads. So there are two types of terminal pads, the fully exposed terminal pads and pullback terminal pads. In fully exposed terminal pads, the terminal ends are fully exposed to all the way to the edge of the package and to the side of the package. Here in these pictures you can see how they look like. And in pullback terminal pads, the terminal ends are pulled back from the edges of the package. So thank you.